todos. Estamos muy alegres de hoy día tener este webinar con el doctor Hiroki Sayama de Binghamton University. Es también el lugar donde yo estudié mi doctorado, así que estoy muy contenta de tenerlo por aquí. El doctor Hiroki Sayama nos va a hablar hoy sobre cómo la ciencia de sistemas puede ayudar a los problemas de planeamiento y toma de decisiones relacionados con el COVID-19. Bueno, en el marco de que nosotros aquí en Perú también estamos haciendo todas las políticas y protocolos para, o recibiendo y leyendo del gobierno esas políticas e implementándolas en nuestra vuelta a clases, en colegios, universidades, así que esta charla va a estar muy interesante. El doctor Hiroki Sayama es director del Center of Collective Dynamics of Complex Systems y es profesor también del Departamento de Ciencias de Sistemas e Ingeniería Industrial de la Universidad de Binghamton. Tiene experiencia enseñando e investigando sobre ciencias e ingeniería de los sistemas complejos, ciencias de las redes, ciencias sociales computacionales, simulación y modelamiento matemático, inteligencia artificial y ciencias de la computación y de la información. Y también nos va a explicar un poquito de qué se tratan esos términos. No todas estas carreras y temas los tenemos también en Perú, así que bueno, vamos ahí a hacer un símil que nos ayudará a comprender. Welcome, Dr. Sayama. It's a pleasure to have you here. So please go ahead.
Gracias, Dr. Bejarano. So good evening, everyone. My name is Hiroki Sayama. It's my great pleasure to have this opportunity to share something that I have experienced as a researcher working in system science to cope with COVID-19. So let me start sharing my screen. I hope this works. Okay, now you're seeing my schedule. That's not what I'm supposed to share. Here you go. I hope you can see it. Let me know if you have any issues with seeing the screen. And please feel free to stop me at any time if you have any questions. Okay, so yeah, thank you. So today's talk is about COVID-19 and also how system science as a discipline. We have the system science graduate program at Binghamton University and also the research center named CoCo, as Dr. Bejarano described at the introductory part. She was actually one of the active participants in CoCo. Thank you. So about myself, because many people actually do not know the system science, and I am also not a system scientist by training either. So here's my brief biography. I graduated from the University of Tokyo, Japan, last century. That makes me feel old. In information science, basically it's a computer science equivalent in Japan. And after that, I switched my research area from mainstream computer science to more interdisciplinary field called complex systems. I did 3 years of postdoc at the New England Complex System Institute in Boston. And then I got my first faculty job back in Japan in the Department of Human Communication. As you start to see, there are no common themes in my research background. And after that, I moved to bioengineering in Binghamton. This was my first appointment here at Binghamton for the first 8 years or so. And then I moved to system science and industrial engineering. And now I am also holding a faculty position at Waseda University in Tokyo in the School of Commerce. As you see, it's everywhere. And I don't really have a core research subject per se, but instead, what I do is to use mathematics and computer simulation to study any kind of system. That is the core essence of system science. So for those who are wondering where Binghamton University is located, we are located here, not necessarily close to New York City, but it's about a 3-hour drive from Manhattan. And it's a very nice place to focus on studying because it's very safe and the living cost is also lower than US average, although we might have really cold winter and snow. So Binghamton University has a very unique program called system science. This is highly transdisciplinary research field, as it might have been demonstrated by my own personal background. So we don't really care about what you study, but instead how we study what you study is the core focus of this area. So we use mathematical models, conceptual models, computational model to understand the model, analyze, optimize, and improve any kind of complex systems. So therefore, this is a subject agnostic research domain. And the key core essence of the system science is the following. We try to understand the natural phenomena. For example, COVID-19 would be one such example, as a system made of multiple components interacting with each other as well as with context. So that kind of the formulation of the real world phenomena or the problem as a system is the first starting point of this field. And then the main focus is not necessarily in each component alone, but rather we pay extra attention to how those components are working together, interacting with each other to create something that is rather unexpected. That's called emergent properties of the system. So that is a systemness of the phenomena you're looking at. And we also care about where is the boundary between the system itself and the outside world. What is the environment? How the system interact with the environment and the context. And through those interactions, system behavior is going to be dynamic, meaning that they change over time. And often the future course of a system behavior depends on its history. That's called the path dependency. So all of these are the really non-traditional compared to the more traditional scientific view, where people try to break down complex problems into pieces and try to understand every piece alone. So rather system science try to put them together and then focus on how the interaction is going to create non-trivial behavior and structures. So in this process, we use a lot of computational simulation, mathematics, and the logic, also. So we use a lot of quantitative process to study the many subjects. So that's basically the summary of a system science. So because this is subject agnostic field, you can study so many different stuff from the mathematical conceptual systems all the way to business and industrial systems. Pretty much anything that you can see in the real world can be game of system science. And here's some of the list of topics we cover in our program. Some of the topics might be really buzzword right now, like machine learning, data analytics, agent-based modeling, sustainability, etc. So we cover a lot of cutting-edge topics in our program. So just a quick advertisement. If you are interested in applying to our graduate program, there will be the information session on Thursday this week at 4 p.m. Eastern time. This is the same time as Peru's time, I think. So if you are interested, let me know. You can also complete all the degree program online. So this is just one slide advertisement. Okay, so now I'm going to move into the more COVID-19 related topic because that's going to be today's major topic. Ironically, last year and this year, when everybody in the globe actually saw how the COVID-19 pandemic unfolded in the global scale, many people start realizing the importance of systems thinking and the system problem solving. Because like this kind of curve, you see the exponential growth. Before COVID, very few people could understand what it means mathematically. But after COVID, many people actually saw this in their regional and national level of statistics. So now people have a very hands-on experience, what it feels to see the exponential growth, what it feels to be inside the exponential growth process. And so are the time delay, networks, social networks, and supply chain issues, human behavior. We have seen many complex implications of any of those factors that were very difficult to teach before COVID, but after the COVID, it's very easy to teach this, ironically. So this is sadly, it's a very interesting moment for system science that the people are now looking at system science quite drastically right now. So in this talk, I would like to give you the quick overview of what we have been doing in response to COVID-19, specifically in the context of the university campus. The first 4 items listed here are specific to the university campus response planning last year and this year. The last 2 are more like a generic outreach type of activities, how to inform the general public to the nuances of COVID-19 pandemic. So I would like to make it these disclaimers first. this talk is only about what I know and what I did from the single researcher's viewpoint by using system science. And by no means it's the representative effort of Binghamton University campus, but rather the entire university community actually came together to implement literally hundreds of the actions, plans to cope with COVID-19. So only with such a cohesive effort, coordinated effort at the entire campus, covering so many aspects, we were able to manage the COVID-19 situation. So please take this talk only just a tiny fraction of the university effort at Binghamton. And second, the pandemic situation is very specific to local situations. So whatever I talk about today may have worked in Binghamton, but may not work in other contexts. So please keep in mind that the situation will be very different between Peru and upstate New York and other places. And finally, my understanding of the COVID-19 is from the computer science and the system science viewpoint, which does not mean that I know a lot about the medical or pharmaceutical facts. So therefore, for all the important, accurate information, please seek authentic information source and guidance, like a CDC in the US. There must be the similar agencies in Peru. So don't just grab the information from this informal talk. There might be fake news in my talk. I don't even know. So that's a warning, okay? So basically, I'm not taking responsibility by giving this talk. That's a disclaimer, right? So let me begin. So I'm gonna just go through the topics by topic in the chronological order. The things started like this. On one Saturday, back in March 2020, I received a phone call from President Harvey Stenger. He is the president of our university. Somehow, somewhere, he got my cell phone number. I don't know how. And he spoke to me, Hiroki, can you do the apex prediction of the local county? So Binghamton University is located in the Broome County in upstate New York. Apparently, the county officials contacted President Stenger because they want to do some kind of prediction in the very early stage of COVID pandemic. So they thought the university should have some experts on doing this kind of stuff. And somehow the President Stenger thought I would be the right person to do this modeling. And I said, sure, because I teach dynamic of system, mathematical modeling. Why not? Even though my experience of the epidemic modeling was very, little to none back then. But initially, after I get the phone call from President Stenger in the Saturday morning, I just did the quick, very simple mathematical modeling using Excel. This is a very simple, low-level modeling, but you can still use the very standardized SIR model. It's a very, well-established epidemic model of the equation-based system, susceptible, infected, and recovered model. And I did some parameter sweep to fit the positive case count that were available up to that point, only just a couple of weeks, and the number would be still small, like 100 people. And we were able to fit nicely the model solution to the empirical observation. So this gave us the some very preliminary prediction what is going to happen at Broome County. So this was in the mid to late March, I believe. So we predicted when the peak of the infectivity would happen in that first wave. And we also did lots of parameter sweep because there are lots of the unknown factors. What's going to happen if you wiggle a little bit of parameter values included in that SIR model? And here is the collection of the predictions that are made by changing the parameter values a little bit. So this is essentially sensitivity analysis. Again, it's a very low level, the epidemic modeling, and yet you can still get the clusters of the peak points. And each red dot represents one particular peak of infectivity coming from a bunch of simulation runs. And obviously, this is a very sparse area. The most peak actually pointed out, it should be early to mid-April. That would be the peak. And turns out the reality was not far away from that. The actual first apex, the peak of the first wave in Broome County was happening around April 17 to 18 with 134 active cases, which actually nicely matches the prediction made by this model, even though model itself was very preliminary It was initially created in Excel, but this is still better than nothing. So this was my beginning. And then during the summer, university faced a really challenging situation. I guess many universities also in Peru are facing the similar issues right now. How to safely open the campus without causing the pandemic on campus. And this was actually a very challenging task because in the middle of the summer 2020, or maybe early summer in 2020, like June, July, nobody knew what the COVID-19 was, even though we have lots of cases already, but there are very little information about how it spread in the population. What are the key, the transmission channels? What will be the most effective way to prevent spreading from happening? Does facial covering work? Is there any medication that is helpful for preventing disease, etc.? So basically, we had to make a decision without knowing anything. And this is a challenge. And quite often, you will face similar situation when something like COVID-19 happens. And sadly, in this kind of situation, popular methodologies like data analysis, data science does not help because we don't have data. So this is where system science can actually provide an interesting alternative by taking a lot of information from what is already known empirically, either about COVID-19 or about campus population in general. You can still make the better decisions, informed decisions by using system approaches. So we worked on some of the tasks that are assigned from President Stenger. I'm going to show you one example. So this is the work done by my colleague, Professor Sung-Won Yeon and Sung-Woo Kwon, pictured here. They built a very detailed simulation model of the testing center. Initially, when the university campus opened in fall 2020, like late August, we need to test every single student who are coming to our dormitory. So we, university converted the gymnasium into the big testing center with a lot of space to prevent any infection from happening. So those professors and also their graduate students built a very physically faithful simulation model to optimize the operation of this testing center. So here's I think this works. Okay, maybe sound is too loud. So here you see the animation of the simulation model they built. So this is the physically plausible model of the gym in the Binghamton University. They put the physical movement of the students and how they are being processed by checking in, and then they are sent to the testing sample collection site, and how the collected sample will be transferred to the testing equipment, etc. So by doing this kind of simulation, they checked how many students you can process per 10 minutes or so, and they changed the layout and the staffing, etc. But by adjusting lots of resource allocation, they maximize the operation capability. So this actually helped the university a lot. So as a result, the university was able to process like a 6,000 student testing in just a few days at the beginning of the university. Sorry. And the second similar approach of the modeling to develop a plan for the campus reopening is actually our research team's work to create a very detailed agent-based simulation of a campus traffic so that university administration can tell which part of the university campus would experience a lot of close contact, which classroom, which pathway, inside, outside campus, so that they can tell which part of the campus needs to have a lot of resource investment to do the behavioral intervention. And also we were able to test the effect of population density reduction. How much population should be reduced to avoid the pandemic events from happening? Technically, this is called the multi-layer networks agent-based simulation model. We have layers like this. So this is the actual network structure extracted from Google Earth about how the pathways are structured for vehicles as well as the pedestrian pathways. You can see a little bit of thinner lines inside the campus. This is the main campus where there are lots of classrooms existing, and you can see which way students can walk. And the thicker lines represent the roads for the vehicles. So we simulated the behavior of every single student who are studying on campus in 2019. So I believe Dr. Bejarano was one of the agents we simulated if she was taking class then. And we also simulated faculty members, staff members' presence, their commuting patterns, etc. So this is actually a massive data science project, but it's not a pure data science because we simulated the behavior of hypothetical agents. So here are the list of data we incorporated. Obviously, all the data related to students and faculty are completely anonymized. So we don't really know who is whom, but at least we get the official students, the class registration records. So who took which classes and where are they each classrooms. So we get that kind of information from official academic record. And for the students who are living on campus, again, after the complete anonymization, we get which building they are living on campus. So based on this kind of information, together with other the supporting information, we built a very detailed behavioral model of this campus population. So here's a hypothetical agent behaviors we assumed. So this is just the best guess we made. We assumed every student go to every class they attend, they registered, because they are all hardworking students. Nobody actually skips class. That I know, okay, so Dr. Bejarano is smiling. That's true, right? Yes. And then they move from residence to the classroom, and then sometimes they can get the food during the lunch hours by taking the shortest path on the network. And other students living off campus and the staff members, they will arrive by vehicle and then drop their car in the parking lot and then move to their office or teaching places. So we put a lot of heuristic assumptions to make the best estimate what would have happened in the typical Tuesday on the fall 2019. So this is basically similar to the in forensics. You can reconstruct what happened in the crime scene, even though nobody actually saw the actual scene. By using many peripheral information, you want to make the best estimate of what happened in that scene. So that's basically what we did. So here's the actual movie I can play. This is the real simulation model. I hope this transmits well over Zoom. You can see really tiny dots moving around on campus. They are individual students and faculty and staff members. And the blue discs that are growing outside campus, they show the parking lot occupancy rates. And the green discs inside campus, they show the number of students that are occupying each building. And you see when there's a big traffic happening, you will see the heat map that emerges and eventually evaporates. That visually shows the frequencies of close contact. In this case, close contact is defined as two agents coming closer than 6 feet apart distance, and they spend at least 10 minutes together in that distance. That was the initial definition of close contact set by the US CDC. So we used the same criteria. And I'm going to repeat this one more time so that you can watch it again. Yes, starting in the morning, people come to the campus and they start going to the office and the classrooms. Classrooms gets bigger and bigger. You start to see those green discs growing, right? And it's 10 o'clock. This is a busy time. There are lots of lectures happening here in the lecture hall. And during the lunchtime, you see a lot of traffic between those two. This is the marketplace on the campus that actually has a lot of food places. So students go there to get the food, to feed themselves. And other traffic jams happen in this peripheral area because this place, pointed by the cursor, is a place where there are lots of buses departing from. It's a university union. So you can identify which part of the campus would experience the lots of close contact. So this actually informs us quite a lot of knowledge about the typical campus population behavior. Okay, so, and we also did some very simple calibration model by trying to fit the parking occupancy rates with the actual empirical data, because this is something that we are able to obtain from parking management. So the picture on the top is the actual data of parking occupancy rates. The horizontal axis is the different IDs of parking lots. And the vertical axis shows time in the day. And the parking lot were occupied like this in the real data. And we try to match this pattern with the simulation data as much as possible by adjusting lots of parameters. And the correlation is not perfect, but we get about R squared, that is 0.76, 0.77. So we say this is a decent correlation between what happened in reality versus what was simulated in our model. We also used the mathematical formula to count how many close contact would have happened in indoor spaces, because in this simulation model, we really didn't simulate the movement of an individual agent inside the building. So we use this kind of formula to estimate what is the expected close contact by assuming each particle occupied the space. This is a fairly simple formula to estimate number of close contact. By using this, we are able to create a map after you cumulatively aggregate all the contact numbers on the campus. So this is one particular map if the campus population is 100% as usual. You clearly see there is a big C or E-like pattern. That's where the most close contact would happen. And the benefit of creating this kind of model is that you can run hypothetical scenario testing. So in reality, you cannot really remove the population to 50%. But in simulation, you can do it. So what's going to happen if you reduce 50% of agents randomly removed from the system, and you can get this kind of map? Already quite a drastic reduction of the social contact events. And if you go even lower, 25 density, meaning that if you remove 75 population from the campus, the close contact is basically gone. So we can do this kind of testing more systematically. What we did is to run the many simulation in Monte Carlo simulation way from the original population density 100% all the way down to like 12%, and see how the reduction of population density changes the number of close contacts per student per day. And this is the result. It's actually nonlinear slightly. So if everything is purely linear, then 10% reduction population would result in 10% reduction of social contact. If that's the case, the results should have been like this straight line. But there are more benefits you can gain, at the initial stage. By reducing 20%, you get more than that. So from the purely economical perspective, you can see where there is a trade-off, stops. See here, this line, the parallel to the 45 degrees line, this tells you that around 40% to 45%, that's when the investment costs more than the benefit you're going to get. So that would be the economical decision-making point. But this is not the economy. You need to consider the epidemics as well. So you can also consider another way of interpreting this. In epidemics, many people know R0, R0. So this is a basic reproductive number, which means that what is the average number of new patient one patient is going to create during this his or her infective time. So this can be written down as a number of days they are infected versus number of close contact they typically have per day times what is the average infection probability per contact event. So we estimated very conservatively that number of days when they are infected would be 4 days, even though this is actually much shorter than, much shorter in reality. And also the infection rate we estimated to be 5%. Again, this is the very conservative, overestimated rates. By putting those parameter values though, you can identify what would be the maximum number of close social contact you could allow to happen per day per student. It turns out to be 5, and this is the threshold. We can say that if the number of close contact is contained below this number, it should be all right. And this nicely coincides with the previous analysis as well. Maybe 40% or 45% will be the safe, and yet you can still let the students engage in lots of the on-campus activities. So we reported this result to the university administration, and together with many other practical recommendations and constraints, they decided to operate the university at 40% population density in fall 2020. So it worked out okay, so we didn't really have any massive campus shutdown during the fall 2020. There are incidents here and there, but overall, we were able to successfully finish the fall 2020 semester without much of the big issue. So it worked well. And of course, all models are wrong. So this is a famous quote coming from George Box. So there are so many missing pieces in this model. So please don't consider this is the crystal ball. So one important issue that we regret we didn't include in this model from the hindsight are the students' behaviors in the evening times. Going classes is not the behavior students do. Students actually go out to the downtown and have a nice drink and party, which we don't have any data. So therefore, we couldn't include that kind of party-going behavior. But turns out that is probably the most important factor we should have included. If students go to the bar, whatever you do over during the daytime is meaningless because they just catch a disease when you go to the bar, hanging out without facial coverings. So that's one of the major limitations of this model. Anyway, so we also did similar agent-based modeling for the epidemic processes to estimate what would be the expected number of students in the different epidemic states, like symptomatic infectious, asymptomatic infectious, exposed but not infectious yet, etc. There are so many stages. And by using this model, we also estimated how many rooms would be needed for isolation and quarantine. So there are many parameter variations tested in this model, and we reported the results to the university administration as well. So regardless of the parameter settings you use, the key important aspect is you should expect to see the initial surge of the infection at the very beginning. When students come to the campus, there will be this kind of peak, no matter what you do. So this is something you should be prepared. And also the number of testing. This has a lot of the effects to what's going to happen on campus, especially when we didn't have vaccination last year. The number of testing was the most important and also costly thing that was effective in controlling the pandemic. But now the situation is completely different. Many people can be fully vaccinated. That's a whole different story. So this applies only to last year. Okay. Just in case, if you are interested in how Binghamton University is doing right now, this fall 2021 semester, the official information is available in our website, university website. So please go there and see what the officials are saying. Basically, we are operating at full capacity, meaning that I also go to the classroom teaching in person, but everybody needs to wear facial coverings. Facial masks is mandatory. And also the students need to be fully vaccinated if they are taking classes on campus. And there are very few exceptions given for medical reasons or religious reasons, but those students need to submit the exception request beforehand, and then they need to be pre-approved to come to the campus. And we also have the regular testing sites. So this is a testing site operating at the beginning of the university campus. We still test unvaccinated students, staff, and faculty on a regular basis, as well as anybody who want to get tested. They can actually make an appointment and come to the testing center. Testing is for free for everybody. And isolation and quarantine space is still maintained on campus, although right now the percentage of usage is very low. And as I said, facial coverings is mandatory anywhere indoors, and except when you are eating the lunch, or if you are working alone in the personal office space. And finally, if any students show some symptoms or they are sick or ill or tired, we provide as instructors as much accommodation as we can, like providing the access to the class by Zoom, or giving some additional assignment instead of the class, so that we can discourage students from coming to the class if they are not feeling well. So these are the things that we are implementing right now. And right now the number is very low, although, so this is the picture I just took this morning. This is the SUNY COVID tracker website. Binghamton University data shows that this is a positivity rate. It came down very low right now, less than 1%, although I'm a little bit concerned right now because of winter, the positivity rate is gradually increasing, and then we'll see what's going to happen. But so far, the last 3 days, we have only 2 positive cases. Over the last 2 weeks, we get only 25 for the entire campus, which has probably more than 20,000 people. So this is actually a pretty low number. So we are doing okay. Other project I would like to mention briefly because we are running out of time. So I also keep visualizing the many data sets of the New York State county level, the COVID-19 activities, and keep reporting this kind of information to the university administration since last April. I still keep doing this on a weekly basis. So this kind of a spatial pattern is very informative. Usually people only look at the statistics at the one particular population, one particular county, state. But when you compare different levels of activities spread over space, then you can easily tell that waves are actually coming or waves are gone. So because epidemic is a spatial propagation process, putting the many different pieces of information together in this kind of visualization is really essential in understanding what is really happening in the pandemic. So especially we are currently monitoring really closely the data of Broome County. I keep visualizing this kind of stuff and reporting directly to President Stenger even now. So you see the number of positive cases moving like this. There are lots of fluctuations, and also the positivity rate of testing has been a really good indicator. So what's happening right now on the university is, even though the population on the university campus is doing very well, the outside campus, the people in Broome County, their vaccination level is still very low compared to the campus population. So we still have quite a lot of number of cases arising every day. So this is somewhat of our concern. Anyway, I'm going to wrap up with showing a couple of animations. I also personally keep producing the animation of the US nationwide COVID activity patterns, as well as the worldwide ones. So here I can show you the animation. I hope you can see it. So these red dots and blue dots represent the number of activities, and the colors show the phase of their pandemic situation. Red means that they are actually growing. Blue means that they are coming down. So this way you can see, let me play it one more time. So this way you can see that there are actually spatial propagations going on. A pandemic is not by any means the isolated event, but you see, for example, in this case, the pandemic starts from south to the north. Right now, this is the most recent pattern. The northeast and the northern part of the Midwest, they have a lot of activities, as well as this mountain area, you see a lot of red. So geographically, the pandemic is very spatial. So this is something we can do in different countries as well. And so here's how the color scheme works. The color is dynamically adjusted. Whenever you see another wave, the maximum level increases. So the color is calculated this way. So whatever value you have divided by the maximum value experienced so far. So by using this dynamic scaling, you can always paint increasing phase with full red and shrinking phase with purple. So this has been proven to be very intuitive and understandable color scheme. And similar things can be done for international level, like this. So this is a nation by nation visualization from the beginning of pandemic. And as you see, this is a fourth wave in India that spreads to the other regions. The US also have the fifth region. Now we are seeing that the big wave taking place in Europe and Russia. So it is very clearly spatially correlated. And luckily right now, the South America, including Peru, is having a really low number, but you can play this back one more time. There's always a wax and wanes. There are waves coming up and then going out, and the waves might be coming back again. So we should be prepared for the next big wave coming. So this movie has been around for many different international media. Some of the German news media actually picked up this to feature the COVID-19 related news coverage. Okay, so there are many other activities I also worked on, such as visualization of the positivity rate within campus, as well as the local community. And we also did some risk assessment of the online classes and in-person classes, we did some statistical comparison, which class format is doing better. And obviously, online class, anybody thinks online class is safer. It turns out on-campus class turns out to be safer. And many students who are taking online classes, they actually have higher positivity rate, probably because they feel comfortable taking classes at home. So they may actually loosen their guard. They go to the bar probably, and they pick up the disease from the local community. So there are many other projects we worked on, but in the interest of time, I'm going to skip those smaller projects. So anyway, so to summarize this presentation, the advantage of the systems approaches can be summarized this way. So system science uses lots of advanced computational technical methods for modeling, simulation, and visualization. They are all very helpful in understanding and making decisions in the complex problems. And we are particularly interested in simulating heterogeneous agents at multiple scales. And this is unique compared to many other scientific disciplines, such as physics, where people consider an element as more or less homogeneous. You have particles or molecules or atoms, and then you consider only a microscopic scale to predict a macroscopic scale, but you jump the important mesoscopic structure, which is key to understand human behavior and pandemic. And we do simulation to understand precisely that mesoscopic structure. And we are also very much aware of space and time and their interactions. So this is really key to understand the spreading process. And also fundamentally, system science is highly transdisciplinary. Therefore, we are used to learning lots of different concepts coming from the broad range of topics. And we also know the difficulties and values of interdisciplinary collaboration, which is really essential if you want to come up with a very well-informed decision that need to consider both medical facts as well as human behavior and educational need for students and faculty. So you need to consider multiple pieces of information together. And finally, system science do care about specific details in the particular situation, rather than just focusing on finding the general, universal results. So many science try to find a general theory, but system science can be used to come up with a very specific solution for the specific need. So those are the summaries of what we think would be most advantageous of being a system scientist. So take-home messages, this is going to be the last slide, is this. So COVID-19 related decision making and planning requires more than data science and machine learning, etc. So nowadays, those are the buzzwords in the business and many other domains. But without the data, you cannot use data science. And there are situations, many situations in COVID-19 that you need to make a decision now, even though there aren't enough data available. So in that case, you need to resort to your common sense, logic, and everyday understanding of how world is operating. So we need to take those common sense and knowledge into account to make it a really good decision. And second, coming up with the mechanistic models like the simulation models I showed you earlier allows you to test what-if scenarios. And this is really essential, rather than just trying to predict what's going to happen next month. Nobody knows. And even if you create a prediction model, the prediction result will be most likely wrong. The more important thing is to try many different scenarios and then get prepared for the many different outcomes. And you need to know the portfolio of the potential outcomes, and you get prepared for any of the scenarios you anticipated. So this is more important than just making quantitative prediction. Even though many policymakers want to say, hey, predict the number next week. Our job is to say, no, that's not how it works, because there are so many uncertainties in this kind of complex problems. And also, as I mentioned, the understanding and the viewing the spatial temporal dynamics is really, really key to reach a deeper insight into the current pandemic situation. So you should, by all means, try to visualize what's happening, not only over time, but also in space. And finally, these things call for mechanistic understanding of complex system problems, for which the system science is really a must-have framework. So we discussed this before the seminar, but the main take-home message is prepare for the worst and hope for the best. So this is what we learned in a very hard way through the last 1.5 years by doing lots of stuff in Binghamton University campus. Okay, so that summarizes my talk. So thank you very much for your attention. And I hope some of the stuff that I presented today might be useful for your university to get prepared for the reopening. I'd be happy to take any questions. Thank you. Gracias.
Thank you very much, Dr. Sayama. Here in the audience, we have a lot of faculty and students from Universidad Peruana Cayetano Heredia. From them, again, thank you for presenting for us. Yeah, I'm going to ask to check if there are questions in Facebook, but otherwise I will also start with a couple of questions that I have myself.
Yes, please.
For example, you mentioned that, of course, things can change. We cannot see under so many uncertainties. Were there moments, specific moments, where you had to adjust, or like in the ongoing planning, where you had to adjust some variables, or the reality show you some other things, and yes, you had to change it? Mm-hmm.
Absolutely, always. So as a computer scientist, you understand we need to spend a lot of time building really complicated simulation models, right? And the next day, situation has changed. We need to redo, or at least we need to make a major revision to the simulation model in one day. That has been a typical cycle, in this kind of effort. So for example, even though we set up some of the assumptions based on what we hope for, the reality is coming from many different angles, like vaccination or testing. So how many testing kits the university can purchase by next week? And there are lots of constraints in terms of logistics. And if your assumption is not really reflected by reality, you need to change the strategy and assumption in a very dynamic way. So always reality wins. No matter how much you insist. No, our model should go this way. The reality tells you the other way. You have to cope with this, right? So it's always changing. Yeah, absolutely.
Right. And another question that I have here is, how much of this behavioral science you think you take or didn't take in these simulations, and how do you think there could be a good approach with behavioral scientists in this way?
Yeah, it would have been very good if we had the behavioral scientists in the team. Unfortunately, we didn't have that. So when we created behavior model students, most of the assumptions are just coming from our understanding of how our students behave. So we didn't really have time to review the behavioral science literature to study, how the college student typically behaves. In fact, there would be very few such studies, right? Like how does college student typically move from one place to another on the college campus? I don't think there are many well-established theories there because it's so everyday stuff. So we need to exercise a lot of common sense and knowledge of our own university student population to build the simulation model on the fly, basically. Because this was done in a very quick way. We didn't really have time to go over many different literature. And also, we didn't really intend to publish this work. And we didn't really have any publication from this. Because it's not done for science, but it's done for the decision-making process. In that sense, this is entirely the service activity for us, to the university. So if we were planning to publish this to the scientific journal, we would have to go over many details of behavior model to validate it, but that was not our plan. So therefore, we took the fastest, quickest approach. Because as I mentioned, no matter how much detail you put by backing up your assumptions with some papers, the reality comes in different directions. You need to change the assumption. So it's better to make the model quick and easy, and they remain very flexible in making adjustment to the system? So the answer is no, we didn't have the behavior science included.
But it would have been good.
Yeah, of course, if we have time and resource, absolutely.
Thank you. And another question here, it says, like, what kind of data sources, if available, could be useful to help the simulations? And I would add, like, was it difficult to access to the data, even though inside the campus systems, information systems, was there any particular information that was more difficult to access, or?
Yeah, so that's a great question. Data is essential in this case. So even though this is the mechanistic simulation model, it is informed heavily by data. Luckily, Binghamton University administration was very cooperative in this effort. So basically, the most difficult part was to know who you should email, but who has what kind of data. You need to ask around to the bunch of people. And then once you discover who is in charge, you can just send a polite email. And they are very cooperative. They just sent me the data in a couple of days. And of course, every single data file is in different format, in the very weird, as you know, very weird rows and columns inserted. And it was not designed for this kind of purpose. So therefore, a lot of data cleaning and fixing lots of issues, that took a lot of time. But getting the data is really easy if you have very cooperative staff members in campus.
And were there specific variables that you needed to collect from several weeks or months, or how different were the periods of time of collected variables?
Yeah, so in this case, in this particular project, we were using only one day. So, or maybe a Tuesday, right? So you need to choose one particular day because class registration are different every day. So we just targeted, maybe Tuesday would be the most busy time, because Monday and Friday, maybe the students have fewer number of classes. But typically Tuesday and the Thursday, as you might remember, it's a busy class time. So we targeted Tuesday of 2019 fall semester. And we collected data only for that particular day. So it would have been nice if we get more day like a Monday through Friday, and then we can actually simulate the entire week instead of one day, if we have more resources. Yeah.
Right, super interesting. And I guess maybe one last question that I also have, was all this simulation useful for other goals, other logistic problems in campus?
Yes, I think so, because this is not necessarily epidemic simulation. It's more like a behavior simulation, right? So after all, we get now this kind of really detailed traffic pattern data. So this kind of simulation could be useful for other purposes, such as event planning. If the campus hosts some kind of event and they want to know how the traffic behaves. So this kind of simulation would be very useful for example, physical facilities division. They need to decide where would be the ideal parking lot space and what would be the best way to navigate a crowd moving from one place to another. So this should be very useful for that kind of purpose as well. Yeah.
Thank you. And was it like used already somehow in campus?
No, not if we get a resource, like if I can hire another grad student for a couple of months, I could easily make it more user friendly. But right now, everything is custom made. So yeah, we'll see how it goes.
Right. Thank you. Well, I guess there are no more questions, Dr. Sayama. Well, we are again very thankful for your webinar, and tell us how things happen in Binghamton. What were the calculations and simulations done there? This is going to be very useful for us.
Thank you very much, and I hope everything will go very well in your campus. So please stay healthy and safe.
Thank you very much. All the best for Binghamton too, and thank you for all the audience that came for the webinar. If you have any questions, Dr. Sayama also left around his email, and he's very happy to also have you in the program of system science
Yes.
talk on Thursday, right?
Yeah. So please join us if you are interested.
Yeah, for graduate studies.
Yeah.
Well, in Binghamton.
Yeah.
Thank you very much. We'll see you next time in another webinar from Universidad Peruana Cayetano Heredia, Ingeniería Informática.
Thank you. Bye-bye.